Hello everyone. So in this series of videos, no pun intended, we're going to be talking about series convergence, or the convergence of an infinite sum of a sequence. But before we can talk about the convergence of a sum, we need to talk about the convergence of a sequence. So a sequence, defined here, is an unending succession of terms. We can notate a sequence as a sub n equals, which we know as the explicit formula, which you've probably covered in algebra class before. And we can also cover it with brackets a sub n, and we could have limits of n equals 1 to infinity, or in this case of 1 to infinity, we can just not have the limits at all because sequences are usually from 1 to infinity for n. So, what we can do here with these sequences, we can test its convergence. So, when a sequence converges, the infinitieth term, or the term as we get to infinity for a value of n, that sequence is going to equal, that sequence term is going to equal some finite value, which we're going to call L. In other words, that was a very jargony definition there. In other words, if we take the limit as n goes to infinity of a sub n, or the sequence, this is going to be equal to the sequence evaluated at an infinitely far away index. And if this equals L, which we know as a finite term, this is going to mean that a sub n converges to L. If it equals plus or minus infinity or does not exist, then a sub n, we just say that it diverges. So, what can we do with these terms if we know that the sequence converges? Well, we can actually determine what type of convergence is this. Or in other words, what type of bound L is. Because we can say that an L is an upper bound or a lower bound, graphically represented with a continuous function for a sub n, which typically doesn't happen. So this is our a sub infinity, or the term that it converges to. And we can say that a sub n is either this, making L an upper bound, or this, making L a lower bound. So, how can we determine if L is an upper or lower bound? Well, just take a look at these two functions. You'll notice that this function right here is strictly increasing, and this function right here is strictly decreasing. So if we know that this sequence is decreasing, then L is a lower bound. But if we know that the sequence is increasing, then L is an upper bound. So, to determine if this sequence is increasing or decreasing, we don't do derivatives like we usually do in Calculus 1. What we use instead is we use a ratio of terms. More specifically, the ratio of a sub n plus 1 over a sub n. And this is useful because if a sub n plus 1 is greater than a sub n, we can say that that sequence increased in value as we moved 1n. So, how can we tell if a sub n plus 1 is greater than a sub n? Well, that would mean that this ratio is greater than 1, because that means we would have a greater term divided by a smaller term, making this greater than 1. So a sub n will be increasing. If a sub n plus 1 over a sub n was actually less than 1, by contrary, then that means that a sub n is greater than a sub n plus 1, or a sub n plus 1 is smaller than a sub n, meaning that a sub n is decreasing. So now let's go ahead and try to apply this information we have here. We have 4 examples right here, and what we're going to do, we're going to determine the convergence of these sequences, and we're going to determine if this converges, then what type of bound is it? Or in other words, if it's increasing or decreasing. So let's go ahead and start off with this sequence right here. A sub n is equal to n plus 2 over n plus 1. So if we take the limit as n goes to infinity of a sub n, we know that this is obviously the limit as n goes to infinity of n plus 2 over n plus 1. And if you notice, this is just an end behavior of rational functions type of limit. So we just take the leading coefficients, which we know as 1 over 1, and so we just get that this is 1. So therefore, a sub n converges to 1. Now, what type of bound is this? That's what we want to do next. So, we just want to take the ratio, not the limit, the ratio, a sub n plus 1 over a sub n. And we can also call this monoticity, by the way, or if the sequence is monotone. So a sub n plus 1 over a sub n, if we just go ahead and plug in n sub 1 for whenever we see n, we get this is n plus 1 plus 2, or n plus 3, divided by n plus 1 plus 1, or n plus 2. And then we divide that by the original sequence, n plus 2 over n plus 1. And then all you have to do is we can just do some algebraic manipulation here to get that this is n plus 3 times n plus 1 divided by n plus 2 squared, or, in other words, which I'll actually go ahead and write here, this is going to be equal to n squared plus 4n plus 3 divided by n squared plus 4n plus 4. And if you'll notice, this n squared plus 4n is identical for all values of n. But then we have a plus 3 and a plus 4 here. Which one is going to be greater? Obviously, the one with the plus 4. So, if the denominator is greater than the numerator, as we stated before, this is going to be less than 1. Therefore, a sub n is strictly decreasing, making 1 a lower bound. I'm just going to abbreviate lower b because I don't have space to write. So moving on from this one, now let's go ahead and move on to a more complicated example, but it's not exactly complicated, and you'll see why. So if we take the limit as n goes to infinity of this new sequence, we're going to be dealing with the sequence 2 minus e to the negative n, dictated from 1 to infinity. So limit as n goes to infinity of 2 minus e to the negative n, we know that this is just going to be 2 minus e to the negative infinity. Now what is e to the negative infinity? Well, that's just the same thing as 1 over e to the infinity, and 1 over infinity is 0. So this is going to be 2 minus 0, which is just 2. So the sequence converges to 2. Now we want to take that ratio again to see if this is an upper or lower bound. So this is going to be equal to 2 minus e to the negative n plus 1 over 2 minus e to the negative n. And we also know that this is equal to, by exponent properties, 2 minus e to the negative n times 1 over e over 2 minus e to the negative n. So, if you take a look at this e to the negative n is being multiplied by 1 over e, or a term with less than 1. So if you notice, this e to the n over e is going to be less than e to the negative n. Sorry, I should have said e to the negative n over e. So, e to the negative n over e is less than e to the negative n. But don't be so hesitant to put a less than 1 over here, because this is being subtracted from 2. If a smaller term is being taken away from 2, compared to a larger term, this term right here is actually going to be larger. 2 minus the smaller term is going to be larger than 2 minus the larger term. So this is going to be greater than 1 for all n. So therefore, a sub n, which is 2 minus e to the negative n, is strictly increasing so 2 is an upper bound. Alright, now let's go ahead and move on to number 3. A sub n is equal to n to the nth power divided by n factorial. Now this factorial term is going to come up a lot in later series that we'll test. So, let's go ahead and get into this limit. So the limit as n goes to infinity of n to the n over n factorial. If we do direct substitution, well, I mean, not really direct substitution, but if you notice, this is going to become infinity over infinity, or an indeterminate form. Thankfully, we have a list, or an order of magnitude that we can follow to figure out what this limit equals. So, the order of magnitude states that as n becomes infinitely large, the natural log of n is much less than n to the p power, which is much less than p to the nth power. Notice that p is just any value greater than, greater than 1, which is going to be less than n factorial which is going to be much less than n to the nth power. If you notice, n to the nth power is much greater than n factorial as n goes to infinity. So this limit approaches infinity. And I really shouldn't even put an equal sign here. I should put an approaches sign because nothing can equal infinity. So, if you notice that this equals infinity, this sequence does not converge. We say that a sub n diverges. We do not say that it converges to infinity. That's just a made-up saying. That does not exist. It diverges. Okay, so moving on to the last one here. N over n squared plus 10. So if we take the limit as n goes to infinity of n over n squared plus 10, you notice that the degree of the denominator is not much larger. The degree of the denominator is larger than the degree of the numerator. So therefore, this limit is just going to be 0, and behavior of rational functions. So let's go ahead and check if this is an upper or lower bound. But you want to be careful here, because if you notice, n over n squared plus 10 for 1 to infinity is always going to be positive. So we know that 0 is going to be a lower bound, but let's just do the ratio anyways, just to prove a point here. So a sub n plus 1 over a sub n, this is going to be equal to n plus 1 over n plus 1 squared plus 10 divided by n over n squared plus 10. And we know that this is going to be equal to, if we just do the multiplying by the reciprocal, n plus 1 times n squared plus 10 divided by n times n plus 1 squared plus 10n. Now let's go ahead and factor this out and expand to just a polynomial that we can work with. So this is going to become n cubed plus n squared plus 10n plus 10 divided by, and we know that this is going to be, and I'm just going to do this all in one step. So n cubed plus 2n squared plus n plus 10n, which is 11n. Now, we cannot explicitly tell if this is going to be increasing or decreasing here. So what we need to do is we need to plug in a few test points for n. And we can actually go ahead and make this shortcut. We can go ahead and shortcut this process by using a calculator. And if we do use a calculator, we get that for n is less than 3, this is going to be greater than 1 for values of n less than 3, but for values of n greater than or equal to 3, it's actually less than 1. And you could just use a calculator to prove that. So we don't want to focus on the terms less than 3. We want to focus on greater than or equal to 3, because that's going to be infinite, because that's going to approach infinity. This is not obviously approaching infinity. So, as you can see, this is strictly decreasing for n is greater than or equal to 3, which we also call eventually strictly decreasing. For n is greater than or equal to 3. So, that means that 0 is a lower bound. And that's it. That concludes part 0 of this series of videos. Now that we understand what a sequence is, we can actually go ahead and figure out how a series can converge. And we use numerous of tests, which you will see in future videos.